The next problem we consider is called subset sum. In this problem, the input is a set S with m elements. Each element has a size. Okay, so you have sizes S1, S2, and so on up to Sm. Okay, each element has a size. Also, you are given a positive integer b. Okay, we'll assume that these sizes are also positive integers. Okay, you have a set S with m elements. Each element has a size m, and also part of the input is a positive integer b. Okay, the question that we want to answer is this: is there a subset T of S, okay, whose size is b? So this is the question that we want to answer. Now, what's the size of a subset? The size of a subset is just the sum of the sizes of the elements in this subset. Okay, let me define this. So size of T is nothing but the sum of the sizes of the elements E which are in T. Okay, so take all the elements in this subset T and sum up their sizes. This will give you the size of a subset. Now, if you look at subsets in S, each of them will have some size, right? Now, we would like to pick up a subset of S whose size is exactly B. This is the problem. This is the algorithmic problem that you want to solve. And this is the next problem we show is NP-complete. Okay. As before, let's first prove that this problem is in NP. Okay, this should not take us too much time. What would the prover give the verifier so that the verifier can look at an input to the subset sum and conclude and convince himself that in fact it is a yes input. Okay. Now, for a yes input, there must exist a subset whose size is exactly B, right? So the prover just gives this subset to the verifier. The verifier takes this subset, sums up the sizes, verifies that this in fact is B. Okay, and this verification happens very fast. He just has to sum up the sizes of this subset. Okay, so subset sum is in NP. Our next job is to show that subset sum is NP hard. Okay, and to do this, we will use exact cover. Okay, what does it mean that we're going to use exact cover? What we are going to do is this. So we'll assume that there is a polynomial time algorithm for subset sum. Okay, if there is one such, we'll construct a polynomial time algorithm for exact cover. So this polynomial time algorithm for exact cover will take input for exact cover, then it will convert it to an input for subset sum somehow, feed it into this subroutine for subset sum, get an output back, and then give an answer for exact cover. Okay, so let's do this. So we are given a polynomial time algorithm for subset sum. Okay, what we want to do is construct a polynomial time algorithm. Okay, construct one for exact cover. Okay, we want to construct a polynomial time algorithm for exact cover. Okay, so since we are constructing one for exact cover, somehow we should convert inputs for exact cover into inputs for subset sum. Okay, so what are the inputs for exact cover? So let's see, we have exact cover on this side. The input is a set T, okay, and subsets A1, A2, and so on up to am. Okay. What is subset sum? Subset sum has a set S. Okay. There is this positive integer b, and then we have sizes S1, S2 up to Sn. Okay. That these two m's are the same is not a coincidence. I mean, I have chosen this. Okay. Anyway, let's just proceed. Okay. Now, what do we want to do here in XC? We want to pick subsets, okay, to exactly cover elements of the set T. We want to pick some of these so that this set T is covered exactly. What do we want to do here? We want to pick elements of S of size, of total size, say equal to B. Okay. Now, here we have to pick subsets. Okay, it says pick subsets. Here it says pick elements. So, there must be a correspondence. There must be a correspondence between subsets in the exact cover input and elements in the subset sum input. Okay. So, somehow subsets on one side and elements on the other side must correspond. So, I mean, that is the reason why M is, I have chosen M to be the same, because they will be the same. Okay. So, for each subset in the exact cover input, there will be an element in the subset sum input, right. Okay. So, you want to pick subsets here and you want to pick elements here. Okay. So, subsets will correspond to elements. So, let us write this: subsets should correspond to elements. Okay. What is the other thing? The other thing is, here I want to exactly cover elements of T, here I want to pick one of size B. So, somehow exact cover on this side must translate to a subset of size B. Okay. So, this side I want to pick exact cover, this side I want to pick a subset of size B. The crucial thing, of course, is what is B, okay, what is B, and what are these sizes S1, S2, S3 up to Sn. I know that with each element of S, actually what it's a subset of exact cover that corresponds. Okay. How do I pick these sizes to make sure that an exact cover on one side corresponds to a subset of size B? Okay. So, this is the problem that we would like to solve now. So, to solve this, let us do a small switch. Okay. So, we will look at a problem which is very related, and then we will show that a solution to this problem can be transformed, I mean, is exactly what we are looking for. Okay. The problem is this. So, you are given a multiset M. Okay. So, what is a multiset? A multiset is like a set, except that elements can be repeated. Okay. You have multiset M. This has k distinct elements. Okay. Let us say x1 and so on up to xk. Each element occurs at most L times. Okay. Each of these can have at most L other copies of itself. Okay. And we are given a positive integer L. Okay. Now, what do we do with this? What we want to do is assign. So, the problem is this. So, assign sizes to each distinct element to x1 up to xk such that the only way to pick a subset of size L, okay, from M is to pick one copy of each element. Okay, let's see what this means. So you have a multi-set. Okay, there are k elements and there are L copies. There could be L copies or perhaps less. Okay, there is at least one copy and at most L copies of each element. And there is a positive integer L. Okay, this positive integer is not given to you. Okay, so let me clarify. This is a positive integer you will have to fix also. Okay, now what you want to do is give sizes to these elements x1 to xk. I want to give some sizes. I also want to fix this positive integer L so that when from this multi-set, if I pick any subset, okay, this subset can also be a multi-set. Okay, so if I remove any subset so that the size is exactly L, then it must be the case that I have picked exactly one copy of each element. Okay, one copy of x1, one copy of x2, one copy of x3, and so on up to one copy of xk. Okay, then we at least know that what L should be, right? L then should be size of x1 plus size of x2 dot 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 up to size of xk. I mean, this we know because when I pick a subset of size L, I must get one copy of each element and nothing else. Now these sizes have to be picked in such a way, okay, that any other subset of size L, if I pick any other subset, that must also contain one copy of each element. If I put two copies of any element, the size of such subsets cannot be L. Okay, so this is the goal. Okay, so how do we do this? So let's see. Okay, so we have elements x1, x2, let's say x3, and so on. Now let's just focus on the first two elements. We'll just look at x1 and x2. So without loss of generality, I can say that x1 has size 1. Okay, so size 1. Okay, we have at most L copies of each. Right. Let's say this is of size 1. In fact, what I want is the sizes to let's say increase. Okay, x1 is the smallest size, x2 is the next one, x3. So I'm going to assign them in increasing order. Okay, x1 is of size 1. What can be the size of x2? Right. So let's look at x2. So size of x1 is 1. What is size of x2? Can it be 1? Clearly not, because if its size is 1, I can always replace a copy of x2 with a copy of x1. Can it be 2? Well, not really, because if I could replace x2 with 2 copies of x1, then I'm again failing. You know, so somehow the size should be such that I should not be able to replace x2 with some copies of x1. Right. So I guess the smallest we can take is let's say L minus 1 or L. If I take L, the way to do it, the way I could replace x2 is with all of x1. Okay. Let's just look at the 2 element case. Okay, supposing I just had 2 elements. Okay, so I just had x1 and x2. Supposing x1 I said had size 1, x2 has size L, okay, and my capital L has to be 1 plus L. Now what can we do? Well, if I pick a subset of this size, I cannot do it only with copies of x1, right? There are L of them, so the total size is L, so I cannot pick something of this size. Okay, this is my set S using only x1. So I will have to pick at least one copy of x2. Good. So if I pick one copy of x2, then this L goes out of the picture. Okay, and now, well, I have one, and the only way to fill this is to pick one copy of x1. So if my sizes are 1 and L, and capital L is 1 plus small l, then the only way to pick a subset from this set so that the size is 1 plus L is to pick one copy of x1 and one copy of x2. There is no other way we can do this. So let's see if we can generalize this, right? So supposing we had 3 elements, x1, x2 and x3. This, well, we'll still retain it as L. What do you think we should put here? Well, there are L elements here, each of size L, that gives L squared. So maybe L squared is a good bound here. Okay. Of course, anything larger than L also will work here. Okay, you can check that again. Anything larger than L will also work. Similarly, something larger than L squared may also work. But let's just check this. So L is nothing but 1 plus L squared. Okay. This is when the set S has 3 elements. Now, okay, if I just took x1 and x2, the total size I will get is L times L, which is L squared, plus 1 times L, which is L, right? I can only get L plus L squared, which means there must exist at least one copy of x3 in capital L. Okay, so there must exist one copy of x3. There cannot exist two copies of x3. Okay, that I can make sure by stating that 1 plus L squared should be less than 2L squared, and for reasonable L's this is satisfied. So I can just pick. I can do this. Okay. Otherwise, you pick L prime, okay, to be maximum of this L and some other constant so that this is satisfied. Okay, we'll just assume that this is satisfied. Okay, so I have to pick one copy of x3. Now we are down to 2 elements, one of size 1, the other of size L, and it's the same argument. Okay, the only way I can do this is to pick one element of size L and the other element of size 1. Okay, so to pick a subset of size capital L, the only way to do it is to pick one element of size L squared, one of size L, and one of size 1, which is one copy of each element. And in fact, a straightforward generalization of this actually works. So I have k elements. I pick the size of xi to be L to the I, and capital L to be 1 plus L and so on up to L to the k minus 1. Okay. Yeah, actually this is L to the I minus 1. x1 was 1, x2 was L, and so on. Okay, so size of xi is L to the I minus 1, and capital L is this. Okay, then the only way to pick something of this size is to pick one element of each kind. Okay, you can't do any which way. Okay. Okay, so what has this got to do? What has this got to do with our set cover? Okay, so before that, it's just easier to prove that exactly one copy of the last element has to be picked. Okay, for that we'll assume that L is less than twice L to the k minus 1. So for large enough L, this is satisfied. Okay. So this L we can take to be the maximum of the initial L that was given and an L which satisfies this. Okay. Okay, so what has this got to do with our with exact cover? Okay, so let's come back and do this. Okay, so in exact cover, the input is a set T. Okay, and I have subsets A1, A2, and so on up to AM. These are the subsets. Okay, now I'll choose L to be the maximum number of times an element occurs in this collection. Okay, so it's the maximum number of times that an element occurs in this collection. Okay, okay. The number of elements is nothing but size of T, which is n. Okay, which was k for us. There were k distinct elements. Here there are n distinct elements, right? And with each collection there are a few elements, and L is just the maximum number of times an element occurs in this collection. Okay, good. So okay, then how do we fix the sizes? So the question is, how do we fix sizes of each of these subsets? Okay, so what we do is we fix the size of these elements first. Okay, and we fix the size of elements like this. Size of each element is L to the I minus 1. Okay, so yeah, so we think of each element of T. Okay, and for each element of T, for the ith element, I fix the size as this. What is the size of a subset, which is what we really want, which is going to be our input? The size of the subset is just the sum of the sizes of these elements, right? So subset sum, so we want to transform this to subset sum. Okay, so we need a set S and an element EI for each subset AI. Okay, for each of these subsets there is an element EI. Now the size of EI, okay, is nothing but the size, sum of the sizes. So we'll think of first fixing sizes of elements of T. Okay, that is fixed like this. The size of the ith element is just L to the I minus 1. So now I can fix size of EI for each x in AI. Remember that x is an element of T. I just add the size of x. Okay, so if it is it's a jth element of T, its size is L to the j minus 1. Right? If it's a jth element in T, it is nothing. The size is L to the j minus 1. Okay, L then is the other thing, or B is nothing but our L, which is 1 plus L squared, and so on up to L to the n minus 1. Okay, now if this set T has an exact cover, supposing this set T has an exact cover, then if I look at those subsets, corresponding to those subsets, I'll have elements in the subset sum, if I sum up these sizes, it will be nothing but 1 plus L squared plus and so on up to L to the n minus 1. Okay. And for the reverse direction, pick any subset of size 1 plus L plus and so on up to L to the n minus 1. The only way to get something of this size is to pick one copy of each element. This ends a discussion of subset sum. So let me just do one small calculation just in case there was a confusion. Okay. So what is 1 plus L and so on up to L to the k minus 1? Okay, this is nothing but L to the k minus 1 upon L minus 1. Okay. So instead of summing this up like this, you can sort of you can calculate it fairly easily. Okay. So this proves that, so calculating the input is easy, and so this proves that subset sum is NP complete. Okay. I think I had mentioned that you need to choose L so that okay, so that this is less than twice L to the k minus 1. Okay, so that can also be done. In fact, you can check that for most L's this will be true. Okay. Okay, so just check that this is true, because if you just multiply it out, you get that L to the k minus 1 is less than twice. I just multiply these two, right? So twice L to the k, okay, minus twice L to the k minus 1. Okay, so I'll need L thrice. Okay, so yeah, so I have I have 2 L to the k minus 1 should be less than L to the k. So you can check that for reasonable values of k this is true. Okay, for L 3 or 4 it's true. So I can just take some L which is larger than that. Okay. Yeah, so that was one thing which I had not completely covered. Proves that subset sum is NP complete. And the last problem we have in this series is called partition. Okay, it's somewhat similar to subset sum. So the input, so it's called partition. Okay, the input is a set T, sizes T1, T2, okay, Tn. Okay, the question we would like to ask is there a partition of T into subsets, let's say S and T minus S. Okay, so partition of T into two parts, which is S and T minus S, such that the size of S equals size of T minus S. Okay, so this should be exactly half size of T. So can you partition it into two parts, both of which have exactly equal size? Okay, again, the size of a subset is nothing but sum of the sizes of the elements in the subset. So can you partition these into two parts so that the size of both are equal? Okay. Firstly, the total size must be even. Okay, if let's say all sizes are integers, positive integers, then the sizes, for instance, it must be even. So let's assume that these things are true. Now this problem is also in NP clearly, because if the answer is yes, then the proof that the prover gives the verifier is just this partition. For each element he tells which part it belongs, right. Now a verifier takes this partition, he verifies that the sum of the sizes of elements in the first partition exactly equals the sum of the sizes of the elements in the second partition. Okay. So this problem is in NP. We would like to prove that this problem is NP hard, and for most problems where sizes are involved, we would like to use subset sum. Okay, so what we'll show is if there is a polynomial time algorithm for partition, there is one for subset sum. Okay, that's what we'll do. Okay, so let's see. So there is an algorithm for partition. Okay, for subset sum, the input are some sizes S1 through Sn, and I have B, and I want to know if there is a subset of size B. Okay, so here's partition. Here I want to know if there is a partition into two equal parts. Okay, so what does this partition say? This means that there must be one of size B and one of size let's say W minus B, where W is nothing but sum of the sizes. Okay, so this asks if there is a partition of this form. This asks if there is a partition where they are both equal. Okay. Yeah, so how do we sort of use this to solve subset sum? Well, here is B. What I am looking for is B and let us say W minus B. What I do is I add let us say two extra elements, one of size L1, one of size L2, so that L1 plus B equals L2 plus W minus B. Supposing I do this, okay, so I take this input for subset sum, I add two more elements, one of size L1 and one of size L2, right. Now I ask, is there a part, and L1 and L2 satisfy this, L1 plus B exactly equals L2 plus W minus B. Now I ask, is there a partition into two equal parts? So I look at this, supposing there is a partition into two equal parts. Supposing, okay, so supposing L1 and L2 land up in different partitions, okay, you partition it into two equal parts. If L1 and L2 are in different partitions, then there is an answer to the subset sum problem, right? There is a yes answer to the subset sum problem. Okay, so if there is a yes answer to the subset sum problem, then there is clearly an answer to the partition, right? I take an answer to the subset sum problem, put L1 along with B and W minus L2 in and L2 along with W minus B, then I know there is an answer. Now if I look at an answer for partition, can I construct an answer for subset sum? Well, I can if L1 and L2 land up in different partitions. Can I force L1 and L2 to land up in different partitions? The answer is yes. Just take L1 and L2 large enough. Okay. For instance, if I take L1, let us say equal to twice W. Okay, if I take L1 to be twice W, okay, then you can check that L1 and L2 will land up in different partitions, because if L1 and L2 both of them land up in the same partition, on the other side the maximum size that can happen is W, right, which is the sum of all sizes, the sum of these sizes of all elements in the set S. Okay, so if I take L1 to be twice W, then L1 and L2, these elements which have sizes L1 and L2, must land up in two different partitions, and the rest of the elements, when I look at the rest of the elements, the ones with L1 must sum to B, the ones in L2 must sum to W minus B, and this is the answer that we are looking for. Okay, so this is then a reduction that shows that partition is NP complete. Okay. So this, let me quickly revise what we've done so far. I have not written a formal proof that partition is NP complete, but I hope that you can fill in the details. Okay. So let's revise what we have done so far. Okay. So Cook told us that SAT is NP complete. Okay. And then we use this to prove that VC is NP complete. Then we showed that 3VC is NP complete. Okay. Okay. Getting from SAT to VC, we first showed that clique is NP complete, and then independent set. Okay, and then VC. Okay, so it was not a direct sort of reduction. We first showed that clique was NP complete, then independent set, then vertex cover, then 3VC, and then we showed that XC is NP complete, and then we showed subset sum, and finally partition. Okay, so let's now look at the problem that we started out with. So remember that you had joined a company and your boss had given a problem where you were given jobs with times, execution times for each job, and you wanted to schedule them on let's say 2 processors, so that the time that the last job finishes was smallest. Okay, supposing this was possible, I mean you actually had an efficient algorithm, let's say polynomial time algorithm for this problem, then you now observe that you can solve partition. Okay, the reason is you just take the input for partition. Okay, the same input you feed into your algorithm, which did the split into 2 processors. Okay, the sizes are just given as running times. Now you look at the partition that your algorithm gives you back. If they are both of the same size, then there exists a partition of the original set into 2 equal halves, right, where the sizes are equal. If not, there isn't. Okay, so the problem that you solve is more general than partition. So if you could have solved that problem that your boss gave you, then you could have solved partition, and by this sequence of reductions that we did, you could have you would actually have constructed an algorithm for all of NP, and that seems highly unlikely. Okay, so hopefully when you give this this set of arguments or this argument to your boss, he'll be both reasonable and intelligent enough to understand and maybe give you a raise instead of firing you. Okay. Thank you. This finishes this module on NP completeness.